In this module, we'll cover the causal inference technique difference in differences. Finally, the fifth causal inference technique in our toolbox, difference in differences. Let's finish strong. Difference in differences is a causal inference technique that works with panel data. Panel data just means that the data has a time component, and stretches over at least 2 periods of time. The method requires data measured from a treatment group and a control group at 2 or more different time periods, specifically at least one time period before treatment, and at least one time period after treatment. In the example pictured, the treatment group is represented by the orange line, and the control group is represented by the blue line. The outcome in both groups are initially measured at some point before the treatment period. Let's just call this the pre-intervention point. The treatment group at time t then receives or experiences the treatment, and both groups are again measured at some point after the treatment period. Let's call this the post-intervention point. Note that not all of the difference in outcome between the treatment and control groups at the post-intervention point can be explained as being an effect of the treatment, because the treatment group and control group did not start out at the same level at the pre-intervention point. The difference in differences technique therefore deducts from this total difference, the difference that would exist if neither group experienced the treatment, represented by the constant difference in outcome. Notice that the slopes, or trends of the orange line and the blue line are equal. And this is the key assumption underlying difference in differences. The parallel trends assumption, which says that the treatment group and the control group in the absence of treatment, follow the same trend and therefore, the difference between the treatment and control group in the absence of treatment is constant over time. What follows from the parallel trends assumption is that any deviation of the treatment group's trend, post-intervention, from pre-intervention, is solely attributed to the treatment. To apply difference in differences, all that is necessary is to measure outcomes in the treatment group and the control group both before and after the treatment. The difference in differences is a simple difference between two differences. Hence the name difference in differences. It is important to note that the counterfactual being estimated here is the change in outcomes for the control group. This means that when we use the difference in differences technique, the treatment group and the control group do not necessarily need to have the same pre-intervention conditions. But for difference in differences to be valid, the control group must accurately represent the change in outcomes that would have been experienced by the treatment group in the absence of treatment. This figure illustrates a violation of the parallel trends assumption, and therefore a misuse of difference in differences. If outcome trends are different for the treatment and control groups, then the estimated treatment effect obtained by difference in differences methods would be biased. The reason is that the trend for the control group is not a valid estimate of the counterfactual trend that would have prevailed for the treatment group in the absence of the treatment. As we see in the figure, outcomes for the treatment group grow faster than outcomes for the control group in the absence of the treatment, so using the trend for the control group as a counterfactual for the trend for the treatment group, leads to an overestimation of the treatment's impact. Policy analysts often use what's called a pre-post analysis to determine the effect of a new law. For example, the state of New Jersey would like to quantify the impact of a new minimum wage law on unemployment rates. And so they might simply sample some low-wage firms like fast food restaurants that would be affected by the minimum wage law, and measure employment before the minimum wage increases, and then at some point again after minimum wage increases. This is the gist of a pre-post analysis. Measure the outcome before the treatment, and then again after the treatment. Then take the difference as the treatment effect. At this point, we're so attuned to what's wrong with such a simple before and after analysis. For example, what if something else changes as the minimum wage law changes? What if there is a federal law that reduces taxes on businesses? What if there is a recession, or an oil shock? You can imagine there being a lot of things going on that confounds the relationship between New Jersey's minimum wage law and the unemployment level in New Jersey. Any of these changes and events, if not controlled for, would bias the results of the policy change of interest. Is there any way, other than controlling all possible things that might change simultaneously with minimum wage law, we can deal with this problem? It would be nice if we had a control group, a group of similar entities existing under similar circumstances that didn't experience the minimum wage increase. One that exhibits common or parallel trends. Sound familiar? In 1994, the economists Card and Krueger published a famous paper that studied this exact same question of whether a change in minimum wage laws in New Jersey affected unemployment. What Card and Krueger used was the difference in differences technique. Note that the ideal experiment would let us observe New Jersey at one point in time, simultaneously in two states of the world. The state with no minimum wage increase. the state with minimum wage increase. Unfortunately, we can't observe these two parallel universes. With difference in differences, we're trying to do the next best thing, by inferring a counterfactual parallel universe where New Jersey experiences no minimum wage increase, by observing what happens in Pennsylvania, which the researchers believe is similar to New Jersey and also doesn't experience a minimum wage increase. Assuming that New Jersey and Pennsylvania have parallel trends over time, Pennsylvania's change in employment can be interpreted as the change New Jersey would have experienced, had they not increased the minimum wage, and vice versa. This is the results from their study. The difference in differences calculation suggests that the increased minimum wage did not induce an increase in unemployment in New Jersey, as standard economic theory would suggest. FYI, the unit of measurement is full-time equivalents, a measure of how many full-time employees there were at the fast food restaurants. Keep in mind that the finding is controversial because it runs counter to economic theory. A minimum wage increase means that the cost of labor goes up, which means that you would see less employment. The exact opposite is what happened in New Jersey, according to Card and Krueger, who estimate that the 80-cent minimum wage increase in New Jersey led to a 2.76 FTE increase in employment. This is the conclusion from the paper. Because they admit that the results run contrary to economic theory, they dedicate most of their paper on corroborating the finding. For example, they provide commentary on why New Jersey has an economy that is closely linked to Pennsylvania. They also talk about why fast food stores in eastern Pennsylvania form a natural basis for comparison with the restaurants in New Jersey, and how seasonal employment patterns are similar in both regions. All of this effort is to explain why the parallel trends assumption holds. Let's move on to another study, this one by the economist, Esther Duflo. Duflo wanted to study how changes in the availability of schooling in different regions of Indonesia impacted the amount of education attained by the local residents, and consequently how that impacted the wages of those affected. And she looked to history, and found that there was a national Indonesian government program called INFRAS, which used surpluses from oil reserves to fund school construction. The administration at the time built close to 61,000 schools in the 6-year period, and most of the construction was targeting remote and rural areas which had low educational attainment. To identify the effect of the school construction program on education and wages, we need to compare and contrast the outcomes of those exposed to the program, i.e. the treatment group, with the outcomes of the individuals not exposed to the program, i.e. the control group. The strategy Duflo uses is difference in differences estimation. The difference in differences estimate, as you already know, compares pre- and post-differences in the outcomes of the treatment and control groups. So you might be wondering, what exactly is the treatment and control group in this study? Duflo defines children born in communities where many schools were built as part of the INFRAS program as the treatment group, and children born in communities where few schools were built as the control group. Note that the INFRAS program was designed to target children that had not previously been enrolled in school. Before the implementation of the program, there were big differences in enrollment rates across regions, which meant that there were regional differences in the intensity with which the program was implemented. Duflo also defines the pre- and post-treatment differences to be based on whether the groups of children affected by the program were young at the time, and benefited from the INFRAS program, or old at the time, and did not benefit from the program. Duflo knew that Indonesian children normally attended primary school between the ages of 7 and 12. Therefore, all children born before 1962 will have been 12 or older in 1974, hence too old to benefit from the program, whereas children younger than 12 in 1974 will have exposure to the program. So basically, we now know the two dimensions of our difference in differences table. It's going to be region of birth, and date of birth. This is the results table from Duflo's paper. It tells us two things about the program's effect on years of education. First, the children in areas of high program intensity had lower years of education and wages, which confirms the fact that the INFRAS program did target areas which had low educational attainment. And second, the difference in differences calculation comes out to be 0.12, which you can interpret to mean that one extra school per 1,000 children increased education by 0.12 years. This is Duflo's summary of her findings from the difference in differences table. And it reads as follows. In both types of regions, average educational attainment increased over time. However, it increased more in regions that received more schools. The difference in these differences can be interpreted as the causal effect of the program, under the assumption that, in the absence of the program, the increase in educational attainment would not have been systematically different in low and high regions. As Duflo later notes, it turns out that this estimate of the causal effect of the inference program derived by difference in differences is statistically imprecise, meaning that it's not a very reliable estimate. Duflo writes, and I quote, "The remainder of this paper will elaborate this strategy to lead to more convincing results." She uses an instrumental variables analysis as her second approach to get, in her own words, more convincing results. Thankfully, you know all about instrumental variables analysis from the earlier module, so feel free to check it out in your own time. Before we forget, let's cover the potential downsides of difference in differences. The first problem is rooted in the parallel trends assumption. The difference in differences technique does not identify the treatment effect if the treatment and control groups were on different trajectories prior to the treatment. The second problem is concomitant treatments, also known as confounding events. The idea here is that there are many laws and programs which are being implemented, so there is of course a good chance that we are picking up the effect of one or more of these confounders and not the actual treatment we care about. The third problem is the idea of there being pre-treatment trends. For example, there is a commonly observed phenomenon called the Ashenfelter dip, where there is a decrease in earnings or employment levels in the periods leading up to a treatment. A pre-treatment dip that is specific only to treated units would create bias in difference in differences studies. The fourth problem is the manipulation of treatment assignment. For example, our subjects in the treatment group may migrate such that the population resident in the treatment group before and after the treatment period is different. Difference in differences is one of the most popular techniques that is being used today to discover causal relationships. Therefore, it's important that we supplement our current understanding of difference in differences with some canonical resources to help us become experts.